All right, so today we're going to continue, and I'm going to go ahead to the next notebook and come back to thinking about math another day. Um, it'll be a short day today as well, but I might actually change the topics for next week. Stay on this a little bit longer, or maybe even look at the TensorFlow library instead, or JAX. Really, I think JAX is going to be or being geared up to be the TensorFlow replacement. So it might be good to learn JAX with everything that's going on. So today's notebook is on broadcasting, and it describes how arrays with different shapes are treated during arithmetic operations. The term broadcasting was first used by NumPy and now is used by other libraries. And I do find it thoroughly confusing. Actually, I wonder if I did this one already. Now my memory is we totally did this one already. My memory is so bad. Okay. Let's do this. Or actually maybe they just copied something from a different notebook. Let's scroll down some. Because I copy my notebooks regularly and other things that I need to do. I don't remember CD scans, so um let's do this. Math can really save your life. It's truly amazing what we can do with imaging technology. I know on Friday when I wrote the newsletter, we were talking about imaging the brain and how AI is really going to help us eventually solve problems like low level blindness. So, um, I'm processing. So, to take reads of the. No, we did do this. And okay, yeah, I'm not crazy. So, we are on this notebook. Ignore me. I don't know what I'm doing. Health outcomes with linear regression. Man, you don't want to be doing this with a headache. I had to code all morning. So we are looking at the diabetes data set, and they're going to do a linear regression in scikit-learn, which makes sense. Done this for that before. Mean squared norm and absolute error. The best coefficient. Adding polynomial features is still a linear regression problem, just with more terms. So additional variable x to calculate the polynomial features, which yeah, that's exactly have that little function. They have a little function, then they fit transform to get those functions and features names. So now we can speed this up. We use NumPy and it compiles the C directly. This would have been helpful for a lot of things. It's a compiler. Never heard about it until, actually, I guess I did, because if I did it before, unless they've updated these and I forgot. But you can use this. I normally just use Dask or Ray. Well, I guess to distribute the workload, I guess, or it's just speeding up the time it takes to run. So that's cool. Thank you for the compliment. I didn't know anyone was watching from India. Oh, that's fun. I can't respond in this platform. I have no idea how to do that. Normally, nobody chats with me during live stream when I'm learning stuff. So appreciate you joining, and I hope you're learning something as you study too. So caveats. Oh, it's 1,000 times faster than pure Python. And so basic vanilla for like using Python is for, okay, that makes that easier to understand. If you use Python instead of, what is it? If you use Python instead of like pandas, then this should be easy to use. So this will show us time again. And really, it is important how long it takes things to run. I don't care what anyone says, like how you choose to format your functions, what package you choose to use. All of that costs money because it all runs on servers. When you're in a production environment and you have a budget to meet, but still have a have to implement something, getting the cost down is key. So here, let's read what they have. So if you use NumPy on whole arrays at a time, it creates lots of temporaries and it can't use the cache. If you use Numba looping through an array time at the item at a time, then we don't have to allocate. Okay, yeah, large temporary arrays and reuse the cache data. So this is with NumPy, and this is the speed, right? No, this is the setup. This is the speed. So this takes 49 milliseconds. And this is just using NumPy zeros random. Now, if you vectorize it, what's this? I guess this is supposed to be Python, but you're still using NumPy. But I guess they mean in the function. This is a pure Python function. Now, and you do a random generation of numbers. Now, this is the same function. There's no difference there. I guess we're measuring this one. So they use NumPy to do it, and that decreases to 35 picoseconds, which is a whole metric lower. Now, if we use a decorator, and we just decorate this function, we get 6 picoseconds. That is pretty impressive, because I would have probably done it the first or the second way, and this speeds up the whole thing. So if they vectorize it and they do it, we save one more picosecond. We didn't go down much more than that. So pretty impressive. Now, if you do the polynomial features, which we did in scikit-learn, but we do in Numba, And I guess it's all about storage is what they're trying to say. Always traverse the data in the order that it's laid out. So column-wise, Fortran, R, Julia, Row, C, C++, Python, Pascal, Mathematica. Turns out that matching, yeah, that makes sense. That's why algorithms are important. Even though I don't remember. I'm thinking of maybe doing the Twitch and like coding a game engine live so that I can really understand deeper software engineering. I do think that a good portion of like data scientists, there's the business end, right? You don't do much but the data analysis, experimentation, running, etc., so forth. But a large part is going to go into the software engineering and developing these things in the next 10 years or so. So you really, and like optimizing on the hardware, which you cannot use your same stuff to optimize on hardware. So you really do need to know. Okay, so we got a train as Fortran array. So guess we're creating a Fortran array. Why? And we manipulate it just for training data. We get the number here so that we can run it. And I guess that's because we're using number. It's better to do it the column wise if that's how it's processing. And then we get the metrics out. Only takes 7 picoseconds. That's fast, man. We still process it with scikit-learn. And you fit it 600 picoseconds. Lasso regression uses an L1 penalty, which pushes towards sparse coefficients, right? The parameter alpha is used to weight the penalty term, and then the cross-validation performs cross-validation over the number of different values for alpha. So linear model, cross-validated, fitted, CV, alpha, out, RESIX, add noise, Huber loss, to change and less sensitized outline. Well, that was easy. Oh, writing our own implementation? That sounds daunting. Like I've never, or at least I don't remember doing this lesson. Actually, I'm not even sure if I got this far down in this specific one. I didn't have to. Like, why would I want to know what it was doing unless I was building it? And I'm typically not a researching data scientist. But again, the times are changing as we move toward more optimization of the hardware. You'll need to know a lot more to be a data scientist these days than you would for when I started over a decade ago. Okay, I can't do this today. No, I cannot look at. I do want to look up QR factorization.
In this video, we'll discuss the QR factorization. The problem is to find Q and R for the QR factorization of the following matrix. What we want to do here is to write the matrix A as a product, Q times R, where Q is an orthogonal matrix, meaning it has orthonormal columns, and R is an upper triangular matrix. Now, this will be possible whenever the columns of A are linearly independent. So our first step will be to take the columns of A and turn them into an orthonormal set. And we can do that using the Gram-Schmidt process. Now, in our previous video on the Gram-Schmidt process, we started off with this same set of 3 vectors here, and we found the following orthogonal set. So I'm going to write here, previous video. If you don't remember this example, you can look back at that video on the Gram-Schmidt process and figure out how we built this set X. We also mentioned in that video that we may want to simplify this last vector here. We could actually scale that by dividing each component through by 2. And I think we should do that here just to keep the numbers a little bit simpler. So this last vector is going to become 4, -2, -3, -3. So at this point, we have turned the columns of A into an orthogonal set. But what we really want is an orthonormal set. So we're going to have to go through, divide each of these vectors, each of these 3 vectors by its length. So the length of that first vector is the square root of the sum of the components squared. So we'd have 1 squared plus -1 squared plus 1 squared plus 1 squared. That gives us root 4, or in other words, 2. So to normalize that vector, we're going to go through and divide each of those components there through by 2. So this is what our orthonormal set is going to look like. That first vector will be divided through by 2. And in a similar way, we can calculate the length of this second vector here to be root 76. So the normalized version of this vector will look like this. And if we look at the simplified version of this third vector here, its length is root 38. So the normalized version of that vector will look like this. I'm not going to worry at this point about rationalizing any of these fractions or simplifying these fractions. We'll do that at the very end of the problem. At this point, we're able to write down our matrix Q. So the columns of Q will just consist of these vectors here that form our orthonormal set. Now let's figure out how to calculate R. Remember that we want A equal to QR. So the trick here will be to multiply on the left by Q transpose. The reason that we do that is that Q is an orthogonal matrix, so Q transpose Q is guaranteed to equal the identity matrix. So in other words, on the right side, we've got IR, which just gives us the matrix R. So we've got this little formula here that reminds us how to calculate R. I think I'll circle the rows of Q transpose here and the columns of A just to make this calculation go a little bit more smoothly, because there are a lot of roots in this expression. So the nice thing about this calculation is that when we grab the first row here, everything's over 2. So we really just need to pay attention to the numerator here. We're getting 1 times 1 plus minus 1 squared plus 1 squared plus 1 squared gives us 4. So it's really 4 over 2. Moving over to the second entry, again, if we just look at the numerators, 1 times 2 plus minus 1 times 1 plus 1 times 1 plus 1 times 1, that's going to give us 3. So that's 3 over 2. And then finally in the top right here, we've got 4 over 2. So we'll simplify these expressions or these entries in a minute. Moving into the second row, we've got 0 over root 76. Then we've got 19 over root 76. And for the third entry, 24 over root 76. Okay, now moving into the bottom row, we've got 0, 0, and then finally 4 over root 38. Now that we found Q and R, let's think about simplifying the entries in these matrices. Top row comes out to 2 3/2, 2. In the middle row, if we simplify this fraction here, 19 over root 76, we can call that root 19 over 2. And in this third entry here, this guy's going to simplify to 12 root 19 over 19. And then finally in the bottom row here, 4 over root 38 is going to simplify to 2 root 38 over 19. So I think I'll label this clearly as R and just highlight that. That's 1/2 of our final answer. And very last thing we'll need to do is just simplify our matrix Q. So we can refer back to the matrix Q that we had written down earlier in the problem, and we now just need to simplify this for our final answer. First column looks fine as is. Second column, we're going to rationalize these fractions to get 5 root 19 over 38, 7 root 19 over 38, and then finally root 19 over 38 for those last two entries. For our last column, again, rationalizing, we'll have 2 root 38 over 19 minus root 38 over 19, and then negative 3 root 38 over 38 for our last two entries. And there we have the simplified version of Q. So there we have our final answer. We found Q and R from the QR factorization, and we've also done the extra work of simplifying both of those matrices at the end of the problem.
Matrix. What is Q? It's an orthogonal matrix. In other words, it has ortho of a matrix, and also why it's useful in least squares. So let's find, suppose A is given as follows. So 2, 2, 1, 3, 4, 1. And the idea is we would like to decompose A as QR. It's a very cute matrix. What is Q? It's an orthogonal matrix. In other words, it has orthonormal columns, and R will be an upper triangular matrix. And could even have it make positive entries, but we won't worry about that today. And how do you do it? Simply, you take the matrix A, its columns, and you apply the Gram-Schmidt process to the matrix A. So remember, A, the first vector is 2, 2, 1. The second vector is 3, 4, 2. Sorry, 3, 4, 1. And just apply Gram-Schmidt to it. So how do you apply Gram-Schmidt? Well, you get first of all an orthogonal basis. So V1 is U1, which is 2 to 1. And remember, whenever you use that vector, you just cross it out, so you're not tempted to use it again. And then, what's the situation? You have this vector 2 to 1, which spans a line, maybe here. And now you have this other vector, 3, 4, 1. And what you would like to do is, so this is U2. You would like, first of all, to squish this vector on this line. In other words, you would like to calculate the orthogonal projection. So this is U2 hat. And how do you construct U2 hat? So this is V1 here. So U2 hat is just, it's a multiple of V1. So something times V1. And to do that, you just do U2 dotted with V1. So U2 hugs V1, and then V1 is so happy, it hugs itself. Okay. And in this case, what this becomes, this is, a 3, 4, 1, dotted with 2 to 1, over 2 to 1, dotted with 2 to 1, times 2 to 1. And again, it has to be a multiple of 2 to 1. And if you calculate that, I believe you get 15 ninths. Let me see. So 6 plus 8, 14 plus 1, which is 15. And 4 plus 4 plus 1, which is 9. So yes, 15 ninths times 2 to 1. 15 ninths is 5/3. So in the end, you get 10/3, 10/3, 5/3. And again, careful, do not rescale this. Otherwise, you get a wrong answer. And then how do you define your V2? It's simply a vector perpendicular to V1, which in this case, it's U2 minus U2 hat. And that was the whole point of orthogonal projections, is to find a vector perpendicular to another one. So V2 is then U2 minus U2 hat, and that's 3, 4, 1, minus 10/3, 10/3, 5/3. And that's just then 9/3.
Is decomposition the same as factorization? I don't know. Yeah, actually, if you factor it, you decompose it. But I'm not keeping up with the math right now. My brain is like, you don't remember any of this. You never liked it. You never enjoyed it. You're insane. I'm not insane, guys. I promise I'm not insane. Okay, so let's stop here and pick up with watching factorization videos and then going back to the code tomorrow. I think that, or I have to go back to the actual vector math. All right, I'll see you guys later.